Today we're going to look at the basics of fossil fuels and fossil fuel production of electricity, especially with the coal burning plant. On top of that, we're going to look at the key concept here being energy density. We're also going to look at energy flow through something called the Sankey diagram, and then if time allows, we'll look at renewable versus non-renewable and the advantages and disadvantages. We just want to get kind of a big picture of what makes fossil fuels so special and so important in the history of our civilization, at least the past century and a half. So let's do a real quick history of human civilizations. All right, so 2 million years ago, humans are around. How do we basically survive? We're hunters and gatherers. Okay, so we're in savannas of Africa, and we move around in bands. We hunt, we gather fruits, nuts, whatnot, but there's no settled areas, at least not very permanent. And then about 8,000 years ago, we have the very, 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 very important invention called agriculture. Okay, happened in the Fertile Crescent. Independently, it happened in China around the same time. And essentially what happens, humans settled down. We still hunt, but we cultivate crops in small towns, and eventually cities can be built around our ability to get food, water, other resources. And then, of course, 150 years ago, we have the Industrial Revolution. Okay, and what this characterized more than anything in terms of our civilization is we had a population shift from agrarian, rural to cities fairly rapidly. I believe most of the population in the world now is in some urban center or in the suburbs or exurbs of it, and our rural populations have dropped. All right, so why did this happen? In 8,000 years of essentially agricultural civilizations, and all of a sudden we become more urban. And we've talked about this more than anything is the discovery and then the century-long exploitation of fossil fuels. Not only do we have a shift in population, but we had an explosion in population, just as we saw on our PowerPoints. Okay, so let's take a look at one of the key technologies that came out of the whole fossil fuel industrial revolution, and that's an electrical power plant. In terms of energy transfers, it's very basic, okay? We use a fossil fuel, coal, natural gas, sometimes petroleum products, and we use it, burn it to produce a high pressure gas. Okay, so that high pressure gas, and it follows the heat engine cycles that we talked about in the last chapter. It turns a turbine. So in a sense, we go from thermal, which ultimately came from solar, right? Fossil fuels are solar in origin. We have, in a sense, mechanical. That's the turbines. And then, of course, a turbine, which is just a giant generator, produces electricity. And that's our final transformation. Okay, so not only do you want to know that descriptively, one aspect we want to understand is how efficient is it, or how much of our energy burned actually goes into what we want out. So we can see right away that if we put in 100 units of a fuel, okay, let's say this is coal or natural gas, all right, and in the ultimate output is right here in 40 units of useful energy. So we want to be able to, in different situations, draw what is called a Sankey diagram, which uses the width. So the width of this flow, this, how do you want to call it? Arrows, indicates, in this case, 100%, 100 units. And then we just, as we lose energy along the way. So here we see a little chunk of it. Notice by the width of that arrow, we lose around 9% wasted in the furnace for whatever reason. The biggest chunk of waste, and this is what you should understand from last chapter, as and again indicated by this fraction of the width. So your widths matter here, okay, is units wasted in cooling towers, right? That's our QL part of our heat engine. You got high temperature over in the burning side, you have a cold reservoir, and a good chunk of the energy is going to flow there. So ostensibly, the rest is going to go to electricity, but then we lose a small amount, but a measurable amount to friction in the turbine. So there's your standard friction causing a loss of energy, and then the net result is 40 units. So again, this width should be 4/10 of the original width. So when you go to do a Sankey diagram, not only have to identify the sources of energy loss, you have to reflect their relative amounts through the width there. So at some point we'll see others that maybe do practice with this. Anyway, so fossil fuel plants, it's important to know how efficient are they. And they're slightly different for each type of plant, but they're not radically different. And as all things go, they're not too bad. Okay, so typical efficiency of coal plants is 35%. And I'm rounding here to multiples of 5. Natural gas is the most efficient at 45 typically, and then this is 40. All right. Not that you have to memorize. You don't have to memorize any specific one, but you should have a general idea. And this is especially for IB and a multiple choice. They might ask which is the following is a efficiency, and you should know it's in the 35 to 40 range. Now, optimal, maximum, theoretical is slightly higher, generally 5 percentage points higher. Okay, so we see that 50%, 40 to 50% efficiency is not awful. It's not great. It's better than an automobile, but it is certainly a lot less than, let's say, your furnace in your home, new furnace, certainly much worse than, let's say, new light bulb technology, etc. Okay, so let's do a simple little problem. Nothing that requires a new equation, but we want to be able to translate from the old one. So let's say we have 3 billion joules of energy burned in an hour. Okay, that's actually fairly low power for a plant. In a natural gas power plant, about how much was lost to degraded energy? Okay, so that's a real quick question to jump to. There's a lot of little things between there. Understanding that this 3 times 10 to the 9th is our usable energy, and from the second law of thermodynamics, we know we're going to have some degraded energy, and then we're going to get our work output. So our general idea is, again, QH goes into work, and then we have some QL, and that's our degraded energy. Okay, so we're looking for QL, and that's helpful there. Secondly, natural gas power plant tells us something about efficiency. So we can choose between 45 and 50. Why don't we go with the optimistic one? Let's say our efficiency is 50%. Okay, actually, looks like in my notes I put 45%, so I take that back. All right, so how do we set that up? Well, we know there's a number of ways we can express efficiency. So efficiency, by definition, is W over QH. But then again, we don't have W per se, and we're looking for QL, so I can rearrange this equation and say that's going to be QH minus QL all over QH. And then for QH, I'm going to put in the 3 billion joules. So if I do the algebra, and I trust that you can do that, what we end up with is that the QL is nothing more than 0.55 of the QH. And that makes sense. In other words, if our plant is 45% efficient, that means we're losing 55% to thermal energy. So if we take 0.55 of the 3 billion, we get 1.65 times 10 to the 9th joules. Okay, so it's a hefty amount, but there's really not much we can do about it, especially when that fuel is cheap and plentiful. Now we can ask, what's the power output of the plant? In other words, how much electrical energy are we getting out? That's our useful work, so that's PW. So we know that by definition, PW is W over T. So our W, if our waste is 1.65, then W is going to be the difference between the QH and that. So that's going to be basically 3 minus 1.65 times 10 to the 9th. And divided by the time. This is an hour, so we convert that to seconds. Okay, and we can punch that out, and we get around 375,000 watts or 375 kilowatts. So a fairly modest, very modest power point. But these are the type of problems you have to be able to do given efficiencies. All right, so let's turn our attention now to the all-important factor that makes fossil fuels stand out, and that is the energy density. So I have here a table that shows energy densities for a bunch of fuels, fossil fuels or otherwise. I don't expect you to memorize these. You don't have to fill them in. They're already filled in for you. We talked a little bit on class. But what we want to notice is that wood is significantly less than gasoline, coal, which is the worst of the fossil fuels, and natural gas is the bestest. All right, hydrogen is ideal, but it's really difficult to make compressed hydrogen. And then we have fission, fusion, and look at mass equivalence. That's antimatter. Look at how huge those are comparatively, but that's a different story. So let's define energy density. In fact, there's actually two definitions. There's something called specific energy density, which I'm going to call ED, and then there's just energy density in and of itself. So the specific energy density is simply energy released when you burn a fuel, or with fusion and fission, something else, divided by the mass. Okay, in other words, it's given in joules per kilogram, or in these particular cases, megajoules per kilogram. Whereas energy density is defined as energy released per unit volume. Okay, for the most part, we're going to worry about the energy per unit mass, but the IB makes a distinction between the two, so I feel I should let you know. So we can ask how much more energy per kilogram we get is contained in coal than wood, and that's pretty straightforward. So we see coal is around 30, depending on the type of coal, minus 18, so we get 12 megajoules per kilogram difference. Okay, that's a kind of a trivial type of problem. A little bit more involved problem. At what rate must coal be burned in kilograms per second? So notice that's mass per unit time in order to fuel a 500 megawatt plant. And we'll assume here, ideal, 100% efficiency. Okay, so what we have to do is combine three measurements in an equation. We have mass burn rate, we have power output, and then we have the energy density. So I'm going to call the energy density, just for argument's sake, H. Okay? So if you work out the units, and I'm going to give you the equation, basically power output, which is joules per second. Okay? In fact, we'll probably work it out right here. So if we want power, which is joules per second, that's going to be related to the mass rate, which is kilograms per second. And then if you look at the energy density, we have in general joules per kilogram. So we see that works out nicely, that power equals the burn rate multiplied by the specific energy density. Now that you're not going to find that equation in the reference table. You've got to be able to work that out dimensionally. It's not difficult to do so. So in this particular case, if I want m dot, that's going to be equal to P over H. So I've got 500 megawatt power plant. That's what my goal is. I'm going to leave the mega there because my H is in megajoules. So they'll cancel out, all divided by 30 megajoules per kilogram. Okay, I'll leave it to show that gives us joules per second, but 500 divided by 30 is, I believe, 16.7. So under ideal conditions, you have to burn 16.7 kilograms of coal every second to give us the power needed for a small city. That's a lot. Now, what if our efficiency is 40%? Well, then it's got to be even higher. So there's a number of ways to look at that, but the simplest way in my mind of doing that is I'm going to say 0.4 or 40% of my mass burn rate is going into what I want, which is equivalent to 16.7. So when I solve for the new burn rate, it's 16.7 divided by 0.4, which is consistent with the idea I got to burn at a higher rate. So this part here always confuses kids where to put the 0.4, so work it out so that it increases from 100%. So this turns out to be 40.17 kilograms per second. So you've got to burn coal at a fairly high rate just to power a 500 megawatt plant. Okay, so I'll finish up here with a graph, right, showing in the USA fairly recently, 2010, and it hasn't radically changed, where our energy, electrical energy comes from. And we see, by and large, it's coal and natural gas. In fact, oil plays a little part, so it's roughly 80% are fossil fuels. And trending-wise, what we see is natural gas is increasing, coal is decreasing. It's a dying industry. And renewables, fortunately, are, if you will, doing this. They seem to be growing at a very rapid pace, but they're still too tiny of a fraction. Okay, so we'll pick up in class renewables versus non-renewables, and then for different ones. CO2 emissions. And lastly, advantages and disadvantages. In fact, you can do this last chart on your own. It's in your book, page 84. So read that, fill it in. You're responsible for it. Most of it's common sense, but some things might be in there that we haven't talked about.